So why should you study the history of science? What's in it for you? There's probably a lot of good answers to that question, but the one I want to talk about today is that studying history can help us see things afresh. What I mean by that is we can get used to things very, very easily. If something's always been there, it's sort of hard to notice. And science is something that we've all lived with all of our lives. It's been there, it was there when you were born. It's probably in the room with you right now. Actually, I'm certain there's some technological stuff in the room with you right now because I'm talking to you via technology. A lot of people have technology on their bodies or in their bodies. It's just kind of everywhere. So that makes it hard to notice. It's hard to appreciate. And it's especially hard to imagine things being different. So we sort of get locked into the things that have always been there, and we're sort of cognitively unable, unless we make the effort, to picture things being different. So studying history is one of the very powerful ways to get out of that kind of locked in perspective. What we can do is, see the progress of something being constructed. So if you go back to the beginning, you can see it coming together step by step. You can also see the world being quite different in history. So, I mean, the world 3,000 years ago was enormously different than the world we're in today. And spending some time in that world can help us sort of get unlocked from the things that we've always been immersed in. So just quickly, for example, we're going to talk today about what makes science possible. And I can't even begin to list the things that would make this thing. So I've got here a picture of the Large Hadron Collider. The Large Hadron Collider is literally the biggest machine humans have ever built. It's 27 kilometers. It's this enormous ring in which they zip little microscopic particles around and smash them together to see what happens. So this thing is one of the great technological and scientific achievements of our time, but it's kind of always been there. I mean, it was finished, they started it up in 2008, but they started building it in 1998. So for many of you, that means that this thing was designed and the construction had been started before you were even born. And if we're going to think about what makes something like this possible, it's very, very helpful to kind of step back and sometimes way back in history to trace out where it might have come from. So to trace out the beginnings of this kind of project. And if we're going to talk about the beginnings of this project, we really have to go way back. So that's what we're going to do today. We're going to start thinking about the very early origins of science. And we're going to try to do it in a kind of semi-imaginative way. So to get this cognitive benefit of studying history, it's not enough to just memorize a bunch of facts. What you have to do is sort of put yourself in that time and place, imaginatively. That's what sort of helps break you out of your current day perspective. So we're going to do that by thinking about what you need to have in place for science to progress. And this is a partial list I've got here, this list of, I call it a recipe here, because in a recipe you can sometimes leave things out, you can sometimes add things in, you can have more of one thing than another. So this isn't a list of things that always have to be present in every scientific project, and there's probably other things that you want in a scientific project. So this is a recipe, as it were, with some substitutions that you could make. But I think these are all crucial things that you typically need for science to happen. So for example, tools for observations is almost always required. Information technology of some sort, so something to write down your observations, something to record them. Mathematics, to use those observations, to turn them into models and theories. And in a way that I'm going to explain, a philosophical framework actually turns out to be super important. So if that's not clear what a philosophical framework is, just hang on, I'll come back to that at some length throughout this course. And finally, last but not least, funding. You need money to do science. And one of the main reasons you need a philosophical framework is to justify why people should give you money to do science. This has always been a sort of important ingredient to making science go. So I'd like you to think about these things. And I think one of the helpful ways of thinking about them is by doing a kind of Call it a thought experiment. Philosophers love to do thought experiments where we imaginatively go through a scenario. In this case, it's a kind of historical thought experiment. So bear with me, this is sort of odd, but I think it's a helpful exercise. Now, imagine that you've been transported back in time. Imagine that you've been transported 5,000 years ago, so roughly 3000 BC. And I'm going to pick a time and place for us to be transported back to Skara Brae, which is this is a tiny little village in Scotland. It's been dated somewhere between 3000 and 2500 BCE. It's one of the best preserved Stone Age villages in Europe. So this is a little village. They had maybe 50 people living there, stone houses. They've got little stone fireplaces, stone furniture. They probably lived by, say, growing some grain, but they also raised cows and sheep and fished. So it's a pretty simple life. It's a pretty simple little village life. Okay, so imagine that you've been plucked out of your 21st century life, transported back to Skara Brae in, let's say, 3000 BC. Let's suppose that, the villagers have accepted you, so they're gonna take care of your basic necessities for now. Let's imagine that you can speak to them, so somehow you know their language, but you didn't get to bring any of your fancy 21st century technology with you. It's just the clothes on your back and everything that you know in your head. So imagine that you've settled in a bit. You've got a reasonable life. Your basic necessities are taken care of. They've given you a little stone home. They've invited you into their sort of social world. So your basic needs are set. What you start to think, however, you're, imagine, a big fan of science. You love science, and you're living in this stone village. Frankly, there's not all that much to do. I mean, all of your usual ways of being entertained aren't there anymore. So you start thinking of projects that you might like to participate in. And one of the projects that you might want to do is doing some science. So suppose that you think that you can maybe help out humanity by advancing us along the path towards science, by doing something in this Stone Age village in 3000 BC. What do you do? So you can remember the 21st century. Let's suppose that you don't talk to the villagers much about it, because they would think that's very odd. But you do a lot of, say, stargazing. So at night, you can see more stars than you've ever seen before because there's no light pollution. So you spend a lot of nights, like a lot of people, looking up at the sky. And you think, maybe I should do some astronomy. So astronomy is one of the early sciences. Next week, we'll talk about ancient astronomy. So suppose that you decide that you want to, in your spare time, contribute to the project of astronomy. So what do you do? How would you contribute? So what we've done here in this imaginary scenario is take away all that stuff that we've assumed in our 21st century life, all of the technology, all of the built up knowledge, all of the things that you would draw on to do science now. Imagine all that's gone, and you want to add something to the scientific sort of journey of humanity. What would you do? How would you contribute? And let's take astronomy as our example. So let's go through the list. So what I'd like to do now is sort of go through that recipe and talk about how would you sort of cobble together the bits and pieces you would need to start doing some science. So start from tools for observation. Now, doing astronomy, you could probably do some astronomy with no tools for observation. So here's a research program that you could do tomorrow with no tools. If you just sit yourself down on the same rock every morning and watch the sunrise, you'll see something. I mean, you won't see what it looks like in this picture, but what you'll see is the sun rises in a different place every day, or a little bit different every day. And you could just sitting there on the rock, mark down, say you put a stick in front of between your vision and the sun. You could just mark out where the sun rises, and you would create, with nothing but the rock that you're sitting on and some sticks, a record of where the sun has risen every morning across the year. So this is a picture from somebody's taken a bunch of pictures from the same spot in Mumbai. So that's what you're looking at there. So cool, you could make a record at least of how the sky is different every morning. So every morning the sun rises in a slightly different position, and you could map out where the sun is rising. That's actually a useful observation to have. So as I mentioned before, the people in this village are at least partly living by growing grain, we think. So if they're doing some farming, really important information is when are the seasons changing? So, and the change of the seasons, of course, correlates with where the sun is rising. So as the sun sort of like drifts across the sky, when it stops and starts rising, sort of goes back to where it was rising before, that's when there's a change of season. So you've got the summer solstices and the equinoxes. Those are really important observations. Okay, so hey, maybe you want to do that. Maybe that's a research project that you could get into. But suppose that you've told your Stone Age friends about this. I don't think they're going to be super impressed. So not too far away from Skara Brae, well, okay, not too far away. Google Maps thinks it's 52 hours of walking with a couple of boat rides. But nonetheless, it's an achievable journey, is another site which did this job of marking out where the sun's going to rise already. So here's the Callanish Stones. So the Callanish Stones, 52 hours walking and a couple of boat rides away from your village, are already raised in this field. So these are big stones. These are standing stones. You're probably familiar with Stonehenge. There's a whole bunch of these things, and they're big. Like, a lot of effort went into this thing. The central stone is like 5 meters tall. The biggest stone is 5 meters tall, meter wide, and meter and a half wide, and about a third of a meter thick. So lots of effort went into putting these things up. And as far as we can tell, so I mean, what we have right now is just kind of the stones. We don't have a continuous history of what they were used for. But when you look at these kinds of constructions, kind of all over the world, what you find is that the stones really nicely match up with things like where the summer solstice sun will rise. So the summer solstice is the longest day of the year, and that's really important. If you're a farmer, you need to know when the days are going to start getting shorter. And these stones, you know, the where the sun rises on the summer solstice very often lines up with where the stones are planted in the ground. So if your initial pitch to your Stone Age friends is, I'm going to figure out when the summer solstice is, they're probably going to laugh at you and say, yeah, we know when the summer solstice is. We've got these humongous rocks all lined up to measure and help us recall when that happens. So this is a kind of permanent calendar / observatory that they've undoubtedly would have heard of if not have a smaller version somewhere nearer by. So, I mean, the very large version lasted 5,000 years. Much smaller versions could easily have been built and be sort of more ubiquitous. So they're not going to be super impressed with this as a research project. If you're going to start science, if you're going to kickstart science, you probably need something more elaborate, more involved than just figuring out when the longest and shortest days of the year are. So, I don't know, maybe this will impress your Neolithic friends. So you want to do something more specific. So, for example, maybe you've studied some history of science, you know a little bit about ancient astronomical tools. So this is a Dipotra, I think that's how you say it, Dipotra, which is a kind of old tool for observation. And this one may well impress your Neolithic friends, because this wasn't invented until about the 3rd century BCE, which is several thousand years in the future from where you are. So it's a way of making astronomical observations. It's basically just a tube. Well, okay, so if you see this image, what you can see is there's 2 little holes on the very top. And what you do is sight through those holes. You sort of choose an object that you're going to point this thing at and line it up between those 2 holes like a sight. And it swivels in 2 directions. It swivels horizontally and vertically. So when you've swiveled it and pointed it at the object of interest, you get 2 observations, and you can locate that thing in the sky. So if you wanted to measure, for example, the position of the moon or a planet or something like that, this is a kind of pretty rough, okay, so it's a rough tool. This is not an exact sort of like observational tool, but it's a rough tool. It's the kind of thing that you could probably build using Stone Age technology if you had the insight and cleverness to do it and the interest. So, okay, fair enough. So the Stone Age folk have scooped you on the Where Does the Sun Rise project. Maybe you want to do something a little bit fancier. Maybe you want to, for example, start tracking the position of the planets, which is another kind of, we'll talk next week about ancient astronomy. Quite a lot of work went into tracking the planets. So suppose that you're tracking, say, Venus or Mars. Those are quite visible by using the naked eye. You're going to sort of track where it is in the sky using your fairly crude astronomical tool. Now you got to write down your observation. So for every observation that you make, you're going to have 2 numbers, and you got to write it down somewhere. You're not going to be able to memorize. In order to like build a model of the movement of the planets, you're not going to be able to memorize every observation you make. It's going to take a lot of observations to kind of build something useful. So you're going to have to write this down somewhere. And in Stone Age Scotland, there's no paper. There's no pencils. There's no laptops. There's nothing, none of the very familiar tools or sort of like information technologies that we have available today are available to you then. Writing has been invented in the world at this point, so it's 3000 BC. There is writing, but it's not near to you as far as we can tell. So it could be the case that they had writing back then, but none of the records seem to have survived. The most advanced writing systems at the time are in places like Egypt and Mesopotamia. So you're going to have to come up with, well, presumably you would use your own 21st century writing system. But even given that you've got an alphabet and a number system, I mean, that's a really helpful thing that you could introduce to them, right? An alphabet and a number system, because you've got those memorized. And all you have to do is teach them how to use an alphabet and a number system. So that would be really helpful. They'd be impressed by that, I bet. But you still have to figure out something to write this stuff on. And what are you going to use? It's unclear. So popular at the time, 3000 BC, were clay tablets. So this is a cuneiform tablet. And what they do is literally take a lump of clay and use a bamboo stick to make these little impressions on it. And the stick is called a stylus. So, and then the clay, so clay is readily available. It shows up all over the world. You can get yourself some clay. You can get yourself something pointy to make impressions on it. And then you bake it in an oven. You'd have to figure out how to make a clay oven that works. But I think that's well within your abilities as a clever and time-rich person back in 3000 BC. So that's one solution. You could also use animal skins. So parchment was a very popular ancient writing surface to use. But then you have to use an animal skin, you clean it and prepare it in various careful ways. It's pretty labor intensive. And then you also need to figure out some kind of ink. So I don't know what you're going to use for ink in Scotland in 3000 BC. So these are the information technology problems that you would face. You got to come up with something. And notice that this clay tablet is not like information dense. You have a big chonky like piece of baked clay, and you're not going to get that much on it, frankly. The information density is low, especially compared to its weight and size. So you're going to have to find somewhere to store these things. The parchment is really hard to get your hands on. Like, animal skins are not flying out of the air. Like, you got to kill an animal and skin it and prepare the skin and all this stuff. So huge amounts of work are going to go into just recording your observations. Okay. So let's imagine, continuing on. So let's suppose you got that solved. Suppose you got the information technology problem solved somehow. I don't know if you're using clay or whatever. All right. So you got they laughed at you when you proposed that you could teach them the mysteries of where the sun's going to rise tomorrow. They thought that was a pretty basic project. So you've gotten more ambitious. Now you're going to try to build a model of where, say, Mars is going to be in the sky. That's pretty ambitious. That's something that they might actually, if you could accomplish that, that's something that your Stone Age friends might actually be impressed by, because that's a tricky thing to do. I don't know how much you know about how planets move in the night sky. If you're like me, you spend almost your entire life in the city. You spend your evenings by the warm light of a television screen or a computer monitor. So I'll start, please don't be offended if you already know this stuff, but like I'll start from the very beginning. So the stars go across every night as the Earth rotates, the stars go across the sky. Good. So all of the stars make a whole orbit around, from our perspective, they're orbiting around us. Now the planets do something basically like that, in the sense that they also kind of go across the sky every night. But every night, they're in a slightly different position relative to the other stars. So what we've got here is a picture of Mars and what Mars does so each one of those photos is like a different day, right? And it's in a different position relative to all of the other stars as they're streaming across the sky on their nightly journey. Mars does some weird loops because of the way that orbits work. So it's not like it's just doing a very simple, regular pattern across our sky. It does some dips and weaves and stuff like that. So it's not trivial to model. So suppose you've got the observation problem solved. You've got your sort of simple Stone Age observation tool. Suppose you've got the information technology problem solved. You've got some way of recording your observations. Now you've got your stone hut stacked high, let's say, with clay tablets covered in your little observations. How do you put them together into a mathematical model? So into a simple model that would describe where you should expect to see Mars on any given night of the year. I'm going to be very honest with you. At this point in the project, I would give up. Because I don't have enough mathematical knowledge sort of stored in my head. Remember, you didn't get transported back with textbooks or a calculator or like whatever. You just have what's stored in your head. And I guarantee I do not have enough mathematics stored in my head to, even given a stack of clay tablets with these observations on them, a picture of how Mars is going to behave in the sky. So nonetheless, ancient astronomers did do this kind of thing. They were able to build models, not the best models, they're not as good as today's models, but they were able to sort of notice that the planets move relative to the stars night after night, B, make these observations, C, record them, and D, build some models of them. So they were able to build kind of generalized mathematical models of how the planets move relative to the stars. And they used things like trigonometry. So here's a Babylonian cuneiform tablet called Plimpton 322. It's from about 1200 BCE, so like several thousand years after our imagined scenario. But and as far as anybody can tell, this is trigonometric tables. This is trigonometry. And if you remember your trigonometry, what you know is that there are sort of like values. So for a given angle, there's a value. And that value is, I figure out what that value is by plugging it into my calculator. There's somebody had to work that value out, and these people had to work it out by hand. So trigonometry seems to be one of the very important tools that ancient astronomers used to turn their observations into models of how the sky behaves. And that's a whole project in and of itself. So you in the Stone Age don't have access to this. I mean, in 3000 BC in Scotland, you don't have access to this Babylonian tablet with the trig tables on it. So if you're going to do this project, you might have to work out the trig tables for yourself. Again, I don't even know what would be involved in building a mathematical model from those observations because I don't know how to do that. So again, this is well past the point where I would have given up on this project and learned how to fish or something. I don't know. Yeah. And like, I think it's clear. I don't know about you, but to me, this all sounds like just incredible hassle. Like, this is so much work to come up with a model of how Mars is moving in the sky. And like, how do you sell the main question for the philosophical framework, as I mentioned before, one of these essential recipes is, how do you sell this to people? How do you sell this as an important enough project to like put all this energy into? But somehow people did it. So here's, for example, what appears to be an observatory in Mexico, in Chichen Itza. It's like an enormous stone building, and there's no cranes, there's no like backhoes to get this done. It's all human and animal power. And it looks like they built this building specifically around, so similarly to the standing stones, built this building around where various planets and other sort of objects in the sky would be at various times of the year. And it seems to be that they did this because the sky had a kind of religious significance for them. So their picture of the universe, their philosophical framework, you might say, which was profoundly both religious and apparently also deeply imbued with this kind of observations of the natural world. So it's a kind of fusion of religious ideas and natural observation, motivated them to put together a whole building around the idea of like finding out where Venus would be at various times of the year. It's just a huge amount of effort that goes into it. And there are various reasons why your sort of worldview or your philosophy or your kind of overall big picture matter to the way that you do science. But the one I want to pick out just right now is that you have to find a reason to be motivated enough to go through all this stuff. Like, it's a lot of work, and which, you know, a religious framework can give you. So this is a reconstruction of Stonehenge. This is a not great CGI reconstruction of Stonehenge as it probably looked when it was originally built. And it looks like, so as far as we can tell, again, this is sort of reconstructions after the fact, but as far as we can tell, it's a kind of mix of both, similar to the complex at Chichen Itza, a mix of both calendar, observatory, and a site for religious rituals. So all three of these things, like making practical observations, making sort of like more empirical scientific observations, keeping track of what day of the year it is, and your religion are all merged together into this complex web. And that's enough, apparently, to motivate people to haul massive stones hundreds of kilometers and build them into this giant ring. So for most of the periods that we're going to be talking about throughout this course, religion plays a crucial role in motivating sort of observations of the natural world. So for the Babylonians, for the people who built Stonehenge, for the ancient Maya and the Aztecs, religion was a reason to do science, not something that was in conflict with. I mean, I'm calling this science, but it's something very different back then, right? It's this mix of observation and religion and practical things like knowing when to sow your crops and that kind of stuff. So that's one way. Political reasons are another good sort of motivator for doing science. So this is a picture from what's called the translation movement. This happened in the Islamic world from somewhere between 700 and 1200 AD. And here we've got a nice sort of mixed political and religious motivation for doing scholarly scientific work. We'll talk more about this when we talk about science and empire, but so at this point in history, the Islamic caliphates, which is sort of like an empire, had expanded massively, right? They've taken in a whole bunch of different cultures, and the translation movement was all about finding important insights, both sort of natural, philosophical, medical, and so on, in the various areas that had come under their political rule, and then consolidating them, translating them into Arabic, which is the language in which the Quran is written. So it's like a sort of like the language, they were trying to make Arabic into a language of learning, and they were quite successful at it by putting out huge amounts of funding and this massive project of collecting various people's knowledge, translating it, synthesizing it, turning it into something that they could use. So part of this was the sort of religious injunction to be learned, to like learn about the world, the natural world. But also it was a good political move. So when you've taken over a whole bunch of different areas, you want to legitimize yourself in the eyes of the people you've taken over. And trying to find out about their culture and integrating it into your culture is a really good way of doing that, and seems to have been quite successful. So political reasons as well. Okay, so all of this boils down to, so there's a bunch of reasons why you need a philosophy to do science, but one of the most important ones is straight up funding. You need money. You need resources of some sort, because all of this is going to take, as we said, a huge amount of work to get any progress on, right? And all of that work is work that you could have been using, time and energy you could have been using for something else, right? So, you're staying up late at night doing your observations of Mars with your bodged together sort of astronomical tool. That means you wake up at noon when you could have woken up at the crack of dawn and helped people with something else. So you need to sell this project to people somehow, right? You need to convince the people around you that what you're doing is important enough to take resources away from other possible projects and put it into yours. And that's been a perennial question all throughout science. We'll look at a variety of ways in which people have answered this question. So what makes science so worthwhile that, it's worth not doing something else? And for pretty much the whole history of science, the answer isn't there's going to be immediate technological benefits, right? So you with your bodged together astronomical tool, you're not going to invent an iPhone next week and be like, look, guys, all that science was worthwhile. It's going to be a really long time until that project pays off. So you need some kind of story to tell people why this matters. So funding, that's another very important recipe. I would almost say this is necessary for science to happen, is some reason why your project is worth funding. Okay, so this has been a kind of, admittedly somewhat strange, hopefully interesting, imaginative project where we're try to think back to the before we were sort of neck deep in science, before we even started this project, or way, way back in this project. As we said, the people in 3000 BC already knew quite a bit about the natural world. So we're just going like way back, not all the way back. And we've tried to do a kind of experiment in our imagination about what it would be like to be there. What would you do if you were back there? Partly as a way of trying to do what history is really good at, which is to get us out of our sort of assumptions and our sort of ways of seeing the world that we were born into. And I would like you to sort of really savor and try to appreciate how much work has already been laid down for us to do science the way we do it today. And the first research report is basically on this topic. So I'm going to ask you to pick a time and place and imagine yourself trying to do a project and tell me what you would do. So keep that in mind. Keep that thinking about that as we go along. Okay. So just to reiterate, we've got this kind of basic recipe for science, tools for observation, information technology, math, philosophical framework, funding. That's more or less the sort of bits that you're going to fill out on that first project. So start thinking about this now if you can. Okay, thanks.